Now welcome back to the second aspect of signal transduction of this chapter, and this is going to be about some target protein X. It's going to be phosphorylated by kinase and dephosphorylated by phosphatase. So the kinase hydrolyzes ATP, and the resulting phosphate is added to the target protein, which we denote by X. And then there is a phosphatase that can deactivate protein X by removing the phosphate. And we will be assuming that the protein concentrations of ATP, ADP and phosphate are constant. So effectively we're looking at this process done by the kinase, done by the phosphatase. The other thing that we note is that the total concentration of the target protein is always equal to the unphosphorylated concentration and the phosphorylated concentration. And the phosphorylated concentration we're going to define as the active concentration of the protein, and the other one will be inactive. Okay, so we want to study the behavior of this small signaling circuit, and again we shall be interested mostly in terms of the input-output relationship, and the input-output relationship is the output concentration, so the active concentration of the target protein as function of the input, and that input will be an activator of the kinase, and let's denote that by A. Okay, so the input is concentration A, and the output is concentration XP. And what I said earlier in the previous lecture is that in this particular case, this circuit is both capable of giving rise to these almost step input-output relationships, but equally well to hyperbolic relationships and relationships that are almost linear. Whereas the previous example that we discussed, where there was a receptor that could bind to a signal which led to a conformational change, that process is only capable of giving rise to a hyperbolic input-output relationship. This is hyperbolic, this is linear, whereas this is step-like. Okay, and in the extreme case, it really becomes a step. Okay? So now we're going to make a model of it. We're first going to write down the differential equation. So we have the x dt, which is the rate of the kinase minus the rate of the phosphatase. And we have the xp dt, which is the rate of the phosphatase minus the rate of the kinase. You may have spotted it already, but if we take the sum of that, then we see that the total rate of change in the sum of the concentrations equals 0. So that is in fact the same relationship as the one that we started with. The next thing we need to think about is what will be the kinetic. So what will be the rate equations for the kinase and for the phosphatase. Here, since the kinase and phosphatase are enzymes, we need to consider enzyme kinetics. It looks like this. And since we have this relationship, we can in fact remove one of the variables. That's what we're going to do. So we're going to remove the unphosphorylated concentration and the the total concentration of the target protein, we're going to denote by xt. Oops. So this is the model that we're going to end up with, and let's think about this for a moment. So if we plot the rate of the kinase and the phosphatase as function of the unknown concentration xp, which ranges from 0 to x total, then what you see is that the phosphatase has xp as a substrate. It's going to rise, and so clearly, so if xp moves in that direction from 0 to xt, then the x direction is the opposite, right? So if this is Vp, then the kinase will go like this. And here we have steady state. Right. Steady state. Where the rate of the kinase equals the rate of the phosphatase, but is unequal to 0. So as a consequence, you'll see that both the xp dt is 0 and the x dt is 0. So we are at a steady state. Now you can ask the question, is that steady state stable? So let's see. So will the system always go to that steady state? Well, it will, because for concentrations of xp lower than the steady state concentration, right, the kinase exceeds the phosphatase rate, so you will get more xp. So for this initial condition you move in that direction, and for that initial condition you move in that direction. So in other words, the system will always go to the steady state value. So this is also what people call a stable steady state. For all initial conditions, the system will go to a steady state. So the concentration that we're going to plot in this input-output relationship will therefore be a steady state concentration. Now, if there is an activator that activates the kinase, then having more activator will increase the kinase, and having less activator will decrease the kinase activity, leading to different steady state values. So having more activator increases the concentration of the steady state in xp. Right. More activator means higher concentrations of xp. So if this is activator concentration 1, activator concentration 2, activator concentration 3, and now we can make a plot. So let's do it in black again, but I guess it's better. It's better visible. It's more visible. So if we would plot the steady state concentration of xp as function of the activator concentration, then we would take activator concentration 1, 2 and 3. So those values, and plot the concentration of xp. So this would be first concentration, second concentration, and the third concentration, for instance. Okay, so this is how you can determine the input-output relationship from a plot where you have the rate of the kinase and the phosphatase as function of the steady state concentration of xp. Okay, so that's the principle, right? And I guess we are familiar with plotting these rate characteristics and identifying the steady state. Now the question is, under which condition is this system going to be stable? And for that we're going to redraw these rate characteristics, but we're going to look at different scenarios. Alright. Concentration of XP on the x-axis. Maximal concentration total. The unphosphorylated concentration moves in the other direction. V phosphatase, V kinase moves in that direction. The phosphatase has XP as the substrate is going to move. So its rate dependency looks like this. Whereas the kinase has X as the substrate. So its hyperbolic curve is going to move like this. Okay. Now we're going to compare this situation to another case. So here we have high values. So high values for Kp and Kk. Okay. So these values, so let me write it down. So the rate equation for the kinase was this one, and the rate equation for the phosphatase was this one. And now we're going to play around with these values. So the Monod constants, the Michaelis-Menten constants, and you can choose them to be large. So then you get this type of graph, but you can also make Kp and Kk small. And then the graph looks more like this. You know? And this is something that you can investigate yourself in Excel, if you would like. Now, in this scenario, the left scenario, if we have different concentrations of the activator, so lower concentrations and higher concentrations, that you see that the steady state slowly changes with the activator concentration. So here activator concentration 1, 2, 3, 4, 5, 6. So when we make, in each case, you add quite some activator, and there is, in each case, sort of a similar increase in the XP concentration, right? Okay? So this means that for a small change in the activator concentration, for all activator concentrations, there is going to be a response in the XP concentration. So this scenario, therefore, looks a little bit to the linear or the hyperbolic case, where all the changes that you can give to the activator concentration leads to changes in the XP concentration. Now, if you do that here, so if we look at this particular scenario and you remove activator, then there are values for activator increases, where the steady state concentration of XP hardly changes, even though you have big changes in A. Then all of a sudden you have large changes in the steady state, and at some point also these steady state changes in A have no effect on the steady state anymore. So in this particular scenario there is a concentration range of A where there is no response in XP at low A values, and at high A values there is also a range of concentrations of A where there is hardly any change in XP. So that is in fact looking at, is mirroring the situation in the step case. So that means that if Kp and Kk are small, then the input-output relationship of the circuit is step-like, whereas if they are high, the input-output relationship is going to be hyperbolic. So now you understand under which conditions the system can give rise to a step-like input-output relationship versus a hyperbolic input-output relationship. And I guess it's good for all of you to play a little bit with this model in Excel. To make these curves, and from this curve construct this curve, and do this for the situation for high values and for low values of Kp and Kk. So we cover this scenario and that scenario. Now, since the previous example of signaling was only capable of hyperbolic input and output relationship, this system is beneficial from a biological perspective because it can lead to this step-like input-output relationship. Okay.